Okay, thanks for watching my video today. Let's introduce a new function called the gamma function, and this gamma function is also called the Euler integral of second kind. Okay? So the gamma function represented by capital gamma is one commonly used extension of the factorial function to a complex number. Meaning, so we know that for factorial function, this factorial function for negative factorial it does not exist, right? For negative factorial, and note that this factorial function is for real number, right? For real number only. So the gamma function is dealing with the extension of this factorial to a complex plane, meaning this factorial function is only for the real part, right? This real part, but the gamma function extends this factorial into imaginary part. This means whole this plane, complex plane, right? And the gamma function is defined for all complex number except the non-positive integer, right? Meaning this n for any positive integer n, gamma n is n minus 1 factorial. This one later on I will prove that. So gamma n is nothing but n minus 1 factorial. This is the relation between the gamma function and the factorial function. Now if you plug here gamma of 0, so 0 minus 1, which 0 minus 1 factorial, which is minus 1 factorial, right? So minus 1 factorial does not exist, meaning from that we see that this n must be greater than 0, right? If you plug here 1 minus 1 factorial, which means 0 factorial is 1, okay? Gamma 1 is 1, and so on, right? Okay, now this is the expression for gamma function by Gauss, okay? So according to Gauss expression, the gamma function is gamma z is called the limit n tends to infinity n factorial into n to the z upon z plus 1, z plus 2, z plus n, while z is greater than 0. Now proof, you have to note this one, n minus 1 factorial is gamma n. So z minus 1 factorial is nothing but z factorial by z, which meaning z factorial is z minus 1 factorial, right? Therefore if you divide by z, so z minus 1 factorial will be z factorial by z. So z factorial by z, which is equal to 1 over z. Z factorial is nothing but this one, right? 1, 2, 3 up to z. So z minus 1 factorial is equal to 1 over z, this one, 1, 2, 3 up to z. So now multiply both numerator and denominator by z plus 1, z plus 2, z up to z plus 1, this one. So z minus 1 factorial is this whole term is nothing but n factorial, okay? N factorial and n plus 1, n plus 2 up to n plus z, same thing, right? The numerator is just the same thing. Divide by z plus 1, z plus 2 up to z plus 1, this one. So z minus 1 factorial is n factorial. Now all these things now divide by n, right? Divide by n z times, meaning n to the z is n plus 1 by n, n plus 2 by n, up to n plus z by n, such that this is nothing but n times, right? No, z times, so z times meaning n to the z. This n to the z and this n z will be cancelled out. Yes, something like this, n to the z into 1 over n to the z, right? Z times. So this is this one, so z times is here putting 1 by 1 here, right? Now z minus 1 factorial is n factorial n to the z. Now this one, n and n cancel, right? 1 plus 1 by n, 1 plus 2 by n, and so on up to 1 plus z by n upon z, z plus 1, z plus 2, and so on up to z plus n. We nearly tried to prove it out, right? Now if I take the limit, as the limit tends here goes, as the limit n tends to infinity, so 1 over n will tends to 0, or 2 by n will tends to 0, and up to z by n will tend to 0, meaning this will be 0. So we are left with only 1, right? This one part is only 1. Therefore, z minus 1 factor is, from the starting, z minus 1 factor is gamma z, right? Therefore, gamma z is equal to limit n tends to infinity n factorial n to the z upon z plus 1 z plus 2 and so on up to z plus n. This whole term is nothing but just 1. So this is the proof for expression of gamma function by Gauss. Okay.